In teaching model number 4, we take a little bit of a detour and we look at a different kind of diastereomer that doesn't involve a ring. These are molecules that involve a lack of rotation because of a pi bond. These are the sorts of diastereomers that were explored in a significant way in first-year chemistry. Let's look at the 4 different structures that are represented here. And I want to highlight a couple of ideas. So the first 2 are considered to be diastereomers. They're considered to be diastereomers because they have the exact same atom connectivity. Note that their names are but2ene and but2ene. And notice that in one case I call the molecule cis and in another case trans. Now we've used those words, those prefixes, for when we have ring structures and when methyl groups are on the same side or opposite sides. We can also use this terminology about a carbon-carbon double bond if there are 2 groups that are identical on adjacent carbons. And we can say, well, are they on the same side or opposite sides? So in the case of the cis here, we can see the hydrogens are on the same side. We could have, of course, also compared the 2 methyl groups. They happen to be on the same side. All you need to have is at least 2 groups that are identical. And again, in terms of the trans, you can see that the hydrogens are on opposite sides. So these are examples of diastereomers, stereoisomers that are not enantiomers. Now you may recall that in first year, we didn't actually refer to these guys as cis and trans, but rather we used Z and E. Now Z and E is a more universal way of indicating the diastereomer, and I'd like you to know how to go about using this technique. So the idea is we would say that it is the Z stereoisomer, or zusammen, meaning together, if the 2 higher priority groups are on the same side of the double bond. So let me show you what I mean by that. And I'm going to change my pen color just to highlight this idea. Start by looking at one of the carbons. I typically work from left to right if possible, and ask yourself what groups are attached to that carbon. And you're going to prioritize according to atomic number. So going down, I see a hydrogen. Going up, I see a carbon. Carbon has a higher priority, so I would label that as 1. Then I look at the next carbon as part of the double bond, and again I prioritize the groups that are attached to that carbon. I see I have a hydrogen and I have a carbon. The carbon wins. Then I look at the relationship of the higher priority groups. I see that they are on the same side of the double bond. And one of the things that I like to do is to, in a sense, draw a dashed line through the double bond so I can look at the sides, if you will. So not a dashed line between the carbons, but a dashed line along the double bond. So I see that the ones are on the same side, and therefore I would refer to this as a Z. In a similar fashion, if we look at our trans molecule, we have ones on opposite side, and we would refer to this as an E. Now at first, you might think that there's an absolute connection between cis and Z and trans and E, but as you will see, it kind of depends on how the prioritization goes. Often, yes, Z corresponds to cis and E to trans, but not all the time. Let's look at one more example. So the next 2 molecules, example of 1,2-dichloroethene, these are again examples of diastereomers. And again, we compare 2 identical groups. So we have a cis and a trans. If I go through the prioritization, I'm going to start off with my carbon on the left, and I'm comparing a chlorine to a hydrogen. Of course, chlorine wins, and then the carbon on the right, chlorine wins. The ones are on the same side. Oh, that's a Z. Therefore, of course, we've got 1 and 1 here, and this guy will be an E. To make sure that you're comfortable in doing this sort of designation, I ask you to turn your attention to the key question number 6. So here you're asked to look at each of these molecules, A, B, C, D, and designate them as E or Z. And then I say, and if possible, label them as cis or trans. Again, you're going to see that E and Z are more universal, but sometimes you can also label a carbon-carbon double bond molecule as cis or trans. Then I ask you to draw the corresponding diastereomer just below the original structure. Well, to speed this up a little bit, I've already drawn the diastereomer for C and D. So I encourage you to pause the video and give these an attempt. So hopefully you arrived at a similar set of answers as this. So molecule A is an E, molecule B is an E, molecule C is a Z, and molecule D is an E, at least for the upper row. And then of course we've already drawn the diastereomers for C and D, and if the top one's Z, well then the bottom one must be E. Now let's go through the examples of A and B together. First of all, I want to be sure that you understand why molecule E can be designated as an E. So I start with my first carbon as part of the double bond. Again, I like to work left to right, and I prioritize. And I see at first I have a carbon and a carbon. So I can't decide yet which has a higher priority. So the idea is then you look a little bit further and see, well, what's attached to that carbon. So on the top here, because it's a CH3 group, I have 3 hydrogens. On the bottom, I have attached to this carbon, and a hydrogen. You're always looking for the first point of difference. And already we can see that we've got a carbon that beats a hydrogen, and then in fact another carbon that beats a hydrogen. So it's pretty clear that the higher priority is, in terms of how I've drawn the structure, below the double bond. In terms of the next carbon, and just to be consistent, I'm going to go back to my purple color and say, okay, I'm considering the next carbon. What we might want to do is actually explicitly draw in a hydrogen to show, yeah, indeed it's there. And now let's prioritize. I think it's rather trivial though. We can see that we've got a carbon compared to a hydrogen, and therefore the 1 is up here. So then dashed line between the bonds, and the 1s are on opposite sides, therefore an E. In terms of the next structure, so what's attached to our first carbon? Well, a carbon and a carbon. So let's spell out a little more carefully what's attached to each of those carbons. So we've got a hydrogen, and a hydrogen. And then down here, we've got a carbon, hydrogen, and hydrogen. Again, the first point of difference, well, here we've got a carbon that can beat any of the hydrogens that are on the top there. So priority 1 down here. In terms of the next carbon, it's actually the exact same kind of comparison. And so without going into too much detail, I will indicate that it's a 1 up here. Therefore, the 1s are on opposite side of the line that goes through the double bond, and indeed, it's an E. Now you can see that for this molecule B, I also called it a trans. And all I'm looking for is the fact that there are 2 identical groups, that is the CH3s, and they're on opposite sides. So for this structure, we can in fact indicate a trans. Whereas for molecule A, all I could say is that it's an E. So you can see that you could not rely on the cis or trans designation for molecule A. In terms of the prioritization for C and E, I'm going to look at my first carbon here. And very quickly I can decide that 1 is going to be associated with the chlorine, because I'm comparing that chlorine to a carbon. Of course, chlorine has a high atomic number. Again, the bromo group will be 1 for the next carbon, because I'm comparing that bromo group to a hydrogen. So the higher priority groups are on the same side, so indeed a Z. And then finally, for this last molecule D, I've got a hydrogen compared to a carbon, so my 1 will of course be below the double bond, and then I'm comparing a bromine to a hydrogen, so the 1 will be above the double bond. 1 are on opposite sides, therefore an E. Now in this case, I can also designate cis or trans. And in this case, I'm comparing the position of the hydrogens, and they're on opposite sides. To finish this little exercise, let us also see how we would convert an E to a Z. So I'm going to look at molecule A. One of the things I would encourage you to do in such an exercise is draw essentially everything the same, at least for the first carbon. Now I'm going to draw my double bond, and then you're simply going to switch the position of the things that are attached to that second carbon. Now, we actually have a word for these carbons that, in a sense, determine the stereoisomerisms. They're called stereocenters. This is not the exact same thing as a chiral center, although a chiral center is a type of stereocenter. Stereocenters are more universal. And so if you switch any two groups about a stereocenter, you get the stereoisomer. So the idea is I'm going to put the hydrogen up here, and I'm going to put the CH2, CH3 group down there. This is my Z isomer. In a similar fashion, I can take my next structure, and I'm going to draw everything the same on the left-hand side carbon, and on the right-hand side carbon, I'm going to switch the two groups. And of course, then I end up with the Z isomer. Of course, that's exactly what I did to come up with the diastereomers for molecules C and D. We'll do more practice in our live sessions, but hopefully this has served as a review about prioritization and also a review of the diastereomers that are associated with carbon-carbon double bonds.